Okay, so chapter 6, we're going to get into bonding, and we're going to look at two main types of bonding. But in general, a chemical bond is the mutual attraction. What's mutual mean? Is it one-sided or does it go both ways? Goes both ways, okay? So mutual attraction means it goes both ways, okay? Between the nuclei and the valence electrons of different atoms that bring the atoms together. What would in the nucleus be attracting the valence electrons? What inside the nucleus would attract valence electrons of another element? The protons, right? Protons give off a positive charge, valence electrons give off a negative charge. So when we talk about the mutual attraction is that the protons are attracted to the electrons are attracted to protons. Okay, so it works both ways. Chemical bonds, we're going to pull those two atoms together. Some chemical bonds are stronger than others, means they'll pull them together with greater strength. They'll remain closer. Some chemical bonds are weaker. Some chemical bonds aren't really even, they're bonds, but they don't really, you wouldn't really think of them as a bond, and we'll talk about the two main types of those. But chemical bonds will pull those two things closer together. They're really held tightly. Okay? So two main types of bonding are ionic and covalent. Okay? And we talked about ionic and covalent compounds. Those names come from the types of bonds found within those compounds. Okay? So ionic compounds are atoms that completely give up their electrons to another element. Okay, and so really you could think of these as a trading of electrons. Right? They both can't be giving up electrons, right? One has to be giving and one has to be taking. Okay, so they are giving up or trading their electrons in an ionic bond. Okay, and knowing what we know about ionic naming and ionic compounds, what do ionic bonds have to be between? What two types of things?
Metal and non-metal.
Good. It has to be between a metal and a non-metal. Okay, or if you want to think of it another way, it has to be between a cation and an anion. Okay, so within an ionic bond, we see a trading of electrons. And ionic bonds are a little bit funky. I think covalent bonds are what we really, really think of and can visualize as the true bond. Ionic bonds are a little bit different in that they're completely trading electrons. So we're going to give it up and give one of them a positive charge and one of them a negative charge, and that positive and negative charge attract each other so much that they're going to stick together like a bond. Okay, and that's kind of how an ionic bond roughly works, and we'll look at that a little bit more in depth later. Okay. A covalent bond, on the other hand, is atoms sharing electrons. Okay, and when they share them, sometimes they share them equally and sometimes they don't. So sometimes they're shared equally and sometimes they're not. Okay, and so when we say share electrons, I think this gives us a little bit clearer picture of what we would maybe traditionally think of as a bond, which means if I've got 6 valence electrons and Cooper has 2, right? We're just going to combine that outer shell so that both of us can think that we both have 8 outer shell electrons. Right? I have 6, he has 2. We're just going to kind of combine those and hang out so that we both have that 8 electron shell, that octet that we like. Okay, so that's kind of more traditionally what we think of as a bond. But covalent compounds are when we share electrons. And what do we know about covalent compounds? It has to be between two what? 2 nonmetals. Okay, so covalent bonds are between 2 nonmetals. We're going to talk about the even and uneven part of a covalent bond. So we're looking at covalent bonds a little bit more specifically now. If we share them equally, if we have our electrons shared completely evenly or unevenly, it tells us it's a different type of a bond. Okay, so let's talk about something called a polar bond. Have you heard of the term polar before? Kind of. Okay, so we're going to look at something called a polar bond, and this is really a polar covalent bond if you want to put that in there. But a polar covalent, I can't spell, I guess, is when we have electrons shared unevenly. Okay, so within a covalent bond, if we have electrons that are shared unevenly, this is considered a polar covalent bond. Okay, and if we have a non-polar covalent bond, what do you think that means? Yeah, non-polar means they are shared evenly. Okay, which is kind of counterintuitive to us, right? Non-polar means evenly, polar means not evenly. Okay, so it's a little bit counterintuitive there, but I want you to get out your textbook and turn to page 176. We're going to use this kind of graphic to help us determine when our bonds are considered polar, when they're considered non-polar, things like that. So I'm going to give you out a handout kind of to go with this. So each of you need to take a handout. We're only concerned with this side of the handout for right now. I made it double-sided, so we'll need the other side eventually. But we're only concerned with the periodic table side. So the handout I gave you is something called the Pauling scale. Okay, and this Pauling scale, which is that half periodic table, gives us the electronegativity value for every single element. Okay, the electronegativity value for every element. Do we remember what electronegativity means? Not so much. Okay, did anyone know what the most electronegative atom is? Fluorine, good, we know that. The electronegativity value tells us how badly an element wants an electron. How badly it wants to take it from another one. Okay, so fluorine is the most electronegative atom, and it has the largest electronegativity value on that table. And some of them are a little bit hard to read, so I'll kind of give you those numbers. You can write them in. Let me see if I can find that in my book here. Okay, what are some of the ones that are difficult to read on your scale? So if I had a bond between hydrogen and sulfur, just based on its electronegativity values, we can determine if it's going to be an ionic bond, a covalent bond, or an ionic bond, a polar covalent bond, or a non-polar covalent bond. Okay, so let's look at the electronegativity values of both hydrogen and sulfur. Okay, what's the electronegativity value of hydrogen? 2.20. And sulfur is 2.58, okay? When we're doing these, we always are going to just take the larger one minus the smaller, right? There's never going to be a negative value for these. So we would take the larger minus the smaller. And we get 0.38, which means it would be what type of a bond? Polar covalent. So they're still sharing electrons, but they're not sharing them evenly. So between those two atoms, which of those would be taking the electrons a little bit more? Sulfur. Right? Sulfur has the larger electronegativity value, which means it wants electrons more than hydrogen does. So within that bond, they're going to just slide a little bit toward the sulfur side. Okay, does that part make sense? Okay. Let's look at a bond now between hydrogen and cesium. Okay, is it ionic, is it polar covalent, or is it non-polar covalent? Bless you. What do we think? Ionic, polar covalent, or nonpolar covalent? What was your final, what was your electronegativity value difference? 1.41. Interesting. Okay. My initial thought would that it would be an ionic because it's a metal and a nonmetal. Okay. But most of the time we're going to find that our bonds are not completely 100% ionic or 100% covalent unless we have the same elements bonding together. Okay. So this one surprised me a little bit, but we see a pretty uneven still distribution of electrons. So which way are those electrons going to be sliding in this case? Toward what? Toward hydrogen. Okay. Pretty uneven. Okay. If we had a bond between hydrogen and hydrogen, what would you be expecting here? Nonpolar covalent. And do we need to even do the math? No, right? If we have two, if you think of it as like a tug of war, right? Hydrogen and hydrogen will both be pulling on those electrons evenly, right? So they should be distributed evenly within that bond. Okay? All right, questions here so far? All right, good. All right, so within covalent bonding, we talked about uneven and even distribution of electrons. Something that we need to think about in terms of covalent bonding is that when they share, okay, so in a covalent bond, they want to share with someone that will get them how many electrons? 8. So they want 8 electrons, which is called an octet. Okay, so they want to share with someone that will complete them, right? They need to complete their octet. They want 8 electrons. So when they're sharing, they need to think about if I have 6 valence electrons and I want to bond with someone that has 3 valence electrons, is that going to be the best option? No, right? So you have to kind of be strategic, or they have to be strategic in what they can bond with and all that kind of stuff. So you want to form an octet, which is 8 electrons. Okay, that's the magic number here, is 8. Okay, so when we have 8 electrons, we complete what we call the octet rule. Okay, so I'm going to give you kind of the definition of the octet rule. Okay, oops. Each atom wants to share electrons so that both atoms contain a total of 8 electrons in their outer shell. And we talked about this briefly earlier, but there's the rule. Okay, the octet rule. Are we completing the octet rule? Most elements follow this octet rule very clearly. Okay, they want to have 8. However, there are some exceptions to the octet rule. Okay, we're going to really focus on ones that really follow the rule. Okay, but there's a few that don't. And I'll kind of show you which ones maybe those are. Okay. So some exceptions that we will see. Boron. Boron is an exception. Okay, and how many valence electrons does boron have? How many? Boron has 3, right? Because it's in group 13 or group 3. It has 3 valence electrons. So sometimes it's okay with maybe not completing its octet all the way, because it can give 3, and maybe it's okay with only bonding with 3 things. Okay, and we'll look at that a little bit more in depth. But boron is an exception. Phosphorus could be an exception. Arsenic could be an exception. One's really in group 13 or group 15. Okay, those are ones that are common kind of exceptions to the octet rule. Okay, we're going to really hopefully focus on ones that follow the rules in terms of bonding and complete the octet, but there are some that could be exceptions. A focus on covalent bonding, and so we're going to look at drawing 2-dimensional structures of chemical compounds that are covalent bonds. Okay, and so these structures are called Lewis structures. Okay? And sometimes you'll see these called electron dot notation. It's the same thing. Okay, I'll always use the term Lewis structure. But we'll see basically these electrons are indicated by dots, which would be why they're called electron dot notation. Okay? So Lewis structures give us a 2D picture of chemical compounds, okay, and their bonds and all that kind of stuff. Okay, we're going to start with really simplistic Lewis structures. They're going to be able to build into a little bit more complicated ones. So we're going to start with the Lewis structure of just a single element. Okay, and sometimes they call this the dot structure because it's only a single element. But let's look at the electron dot structure or the Lewis structure for fluorine. Okay, when we draw the Lewis structures, we're only looking at the outermost shell of electrons. Okay, because the shells underneath the outermost, shouldn't they be full? Shouldn't they be complete? Yes, right? All of the lower shells in an element should be complete. So there shouldn't be anything that needs to happen to those shells, right? So the outermost shell of electrons for fluorine contains how many electrons? The outer shell for fluorine contains how many electrons? 7, right? Because it's in group 17. We need to remember our valence electron rules, right? 1, 2, skip the transition metals, 3, 4, 5, 6, 7, 8. Okay? So fluorine has 7 electrons. So if I'm drawing the dot structure for fluorine, fluorine goes in the middle, and I draw 7 electrons. 1, 2, 3, 4, 5, 6, 7. Okay? We don't spread them out around like a circle. They need to be in pairs when at all possible. Okay? They need to be in pairs if at all possible. Okay? So if I want to draw oxygen, how many electrons does it have? 6. 1, 2, 3, 4, 5, 6. Okay? And this is why I can't go here, just like that, right? Actually, for our purposes right now, it doesn't really make a difference what we do, but usually we don't like single electrons because they're what we call radicals. Okay, but we're not going to get too far into that, so I'm not really concerned with how you do this at this point. Okay, I'm not going to get into that part. Okay, but essentially they need to be in pairs when at all possible. Okay, and these are electron dot structures or Lewis structures for single atoms. We will never do single atoms. I'm just going to tell you that. Okay, I'm just introducing you how we're going to look at drawing bonds now. Okay, so let's say we go back to fluorine, and I want to look at a Lewis structure now between 2 different fluorine atoms, okay, that have bonded together. So if I have 2 fluorine atoms that bond together, is it a polar covalent bond, a non-polar covalent bond, or an ionic bond? Non-polar, right? They should be shared evenly, right? So if I have fluorine, 2 different fluorine atoms, and I want to bond them, I've got my dot structure for both. And I'm going to move this guy over. Maybe. Okay, so now within that bond that forms right here, these electrons are shared. So each fluorine gets to count them as their own. Okay, so do we see how each of those have 7? Right, we're going to put them together. Each of them kind of has one that they want to give up or take or whatever, share them together. This forms a bond, and we would indicate this bond by just a single line. Okay, so now each of those fluorine gets to count those electrons as their own. Okay, so I'm going to redraw this right here. Okay, it's bonded to that other fluorine. So that single line contains 2 electrons. And each of them still have their other 6 valence electrons here on the outside. Okay, does that kind of make sense how they fit together? Okay, and then within that bond contains 2 electrons. So now let's count our electrons to see if we've fulfilled the octet rule. Does each of them get to count 8? Okay, here's 2, 4, 6, and 8 for this fluorine, right? It gets to count both of the electrons in there. So is it happy? Does it have 8? Okay, and what about the other fluorine? It has 2, 4, 6, and 8. Right? They both get to count both of those electrons kind of as their own. So both fluorines have completed the octet rule, which means both have been kind of completed, right? They're both satisfied with this bond. Okay, does that kind of make sense? How they fit together? A little bit, maybe? Okay, I know this is new. I know it seems a little bit crazy, but that's how it goes. Okay? That I want you to know, once we complete this structure, this is our final structure right here. Once we complete this structure, it's called a Lewis structure. So we have one bond, and then these right here are called lone pairs. Okay, so a lone pair is two electrons that are non-bonded. Okay, two electrons that are not bonded. Okay, so this is a lone pair, this is a lone pair, this is a lone pair. You know what I'm saying? It's a pair, so it's got two electrons. Okay, and any unbonded electron should always exist as a lone pair. So it shouldn't have one single electron hanging out by itself. Okay, we should have a lone pair that's unbonded. Okay, so when I say lone pair, that means a pair of electrons that are non-bonded. Okay. Last thing that we're going to check here on our Lewis structure is that the total number of electrons represented matches the total number of electrons that we began with. Okay, so when we bonded these fluorines, each of them had how many electrons to give? Okay, how many total valence electrons did each have?
7.
Okay, so they each had 7. So that means in a total, we shouldn't have lost electrons or gained electrons from anywhere else, right? It's just fluorine that's sharing. So we should have a total of 14 electrons represented in our structure. So if we go through to count, we say 2, 4, 6, 8, 10, 12, 14. Okay, so although that bond gets to be counted for each when they're talking about the octet rule, it still doesn't count as 4 total electrons. It's still only 2 total electrons. Okay, each of them gets to kind of consider them their own, but in total, it still only represents 2 electrons. Okay, is that making sense? Okay. All right, let's try some now. All right, I'm going to give you some rules that we're going to follow, and then we're going to just start doing some practice ones. Okay, so our first rule for drawing Lewis structures. First rule is determine or count, we'll say count, the number of valence electrons in each atom. Then find the sum. Okay, so when we looked at our fluorine Lewis structure, we knew that each fluorine had 7 total electrons to give, right? 7 total electrons in their outer shell. So our Lewis structure had to have 14 represented. So counting valence electrons is the first step for our Lewis structures. Okay, and these steps will seem a little bit crazy for us right now, but they'll make sense when we start putting everything together. Okay, the second step is going to be to arrange our atoms into what we call, or what I call, the skeleton. Okay, so the skeleton is just elements, no electrons added yet. Okay, so you kind of pick which one goes in the middle or on the outside or all that kind of stuff. But the skeleton is elements with no electrons. Okay, and so there's a couple little extra things that go along with the skeleton. Okay, if you have carbon in your compound, carbon always goes in the center of our compound. Okay, so this is what we're talking about. If we had CH4 and I wanted to draw the Lewis structure, that's 1 carbon and 4 hydrogens. So I would draw carbon in the middle, and then I would draw hydrogens on each side of that structure. Does that make sense? That would be the skeleton of that compound. Okay, are we on the same page so far? Okay. So that's kind of one of our rules for our skeleton. Carbon always gets to go in the center. If you don't have carbon, So if you have no carbon, then the least electronegative atom goes in the center. Okay, or you can call it the central atom, right? That's what I'll kind of call it. Okay, last little caveat here is that hydrogen is never, ever, ever, ever a central atom. Okay, why would that be? If hydrogen can never, ever, ever be a central atom, why would that be? How many valence electrons does hydrogen have? 1. So it can only ever bond to one thing, right? It only has 1 electron to contribute. So it can only ever have 1 bond. There's no way it could be in the center. Okay, so it's always an outer element. Okay, so we count our valence electrons, we put it in the skeleton, and there's kind of our things for the skeleton, or some little rules. Okay, questions so far? Okay. Third step is to bond the central atom to the outer atoms. And complete the octets. With lone pairs. Okay, again, I know these rules kind of seem way out there, but when we start doing some problems, they will all start falling into place for you. Okay, so those are kind of our 3 rules. This last step sounds simple, but it can be very complex. We might have to use multiple bonds. We might have to use lone pairs. There's going to be a lot of different things that could happen in this third step. So Lewis structures, the thing I like about Lewis structures is that there's only, usually, 1 answer, okay? And you can always check yourself by counting your valence electrons. The problem is it's kind of a puzzle, so you have to spend a little time putting that puzzle together. Okay, so Lewis structures might not be something that you get right the first time every time, but the good news is that there's always a way to get it right. Okay, so you just have to maybe take a little time and figure out how that puzzle fits together. Okay? All right, so let's try a couple here following our rules. Okay, so let's do the Lewis structure for NH3. Okay, so first thing we do is we count our valence electrons. Okay, so nitrogen has how many valence electrons? 5. And each hydrogen has how many? Right, there's 3 hydrogen and each of them has 1. So we need to have 8 electrons represented in our Lewis structure somewhere. Okay, we want 8 electrons represented in our Lewis structure. Okay, so that's the first step. Second step is to draw our skeleton. Which of these should be our central atom? Nitrogen, right? Because we know hydrogen is never a central atom. When in doubt, right, it's going to be the one on the left. That's your central atom. Okay, when in doubt, it's going to be the one that there's fewer of, or the one on the left. Okay, so don't overthink things like that, right? Nitrogen is, there's 1 nitrogen and there's 3 hydrogens, so most likely nitrogen's got to go in the middle, right? So for right now, we're just going to spread that outer one evenly around. We're not going to get to the 3-dimensional shape just yet. But for right now, we're going to just kind of build our skeleton very evenly around that nitrogen. Okay? Now we bond our nitrogen to each of its outer elements. Okay? How many electrons are found in each bond? 2, right? Technically 1 from hydrogen and 1 from nitrogen. Right? 1 from hydrogen, 1 from nitrogen. So if we were going to look at the electrons within that bond, right, we would say 1 of them comes from hydrogen and 1 of them comes from nitrogen. 1 of them comes from nitrogen, 1 of them from hydrogen, and so on and so on. Okay, so we've used a total of how many electrons? 6. So we have 2 electrons left. We have 2 electrons left. Does hydrogen have a complete octet, right? Can hydrogen have an octet? No, hydrogen's good with just the bond, right? Hydrogen only has 1 valence electron to give. It's good with just 1 single bond. Every other element needs its octet. So does nitrogen have a complete octet just yet? No, it has 2, 4, 6 electrons that it can consider its own. So if I need 8 electrons, I'm just going to add a lone pair. Okay. Can anybody name this compound for me?
Sulfuric acid.
Close. Really close. No. Hydrosulfuric acid. Close. Sulfuric acid would come from sulfate, and this is just sulfide. That's close though. Okay. So H2S. This time it doesn't follow the little mini rule that the first one is the central atom, right? Sulfur needs to be the central atom here. So we have 2 valence electrons plus 6 for sulfur, which means we need to have 8 electrons in our structure. Okay, we draw our skeleton, we bond to each, which means we've used 4 electrons and we have 4 left. Yeah, that's right. So we just do 2 lone pairs. Okay, let me start over. Sulfur has to go first in the center. Our skeleton comes from our hydrogens just going on the outer side, right? We bond our central atom to each hydrogen, which means we've used 4 electrons from those bonds. 2 here and 2 here. Would we agree with that? So we've got 4 electrons left that we have to put on our Lewis structure somewhere. Okay, hydrogen, they can't go on hydrogen because hydrogen only gets to be bonded to one thing. It never gets lone pairs. So it's got to go on sulfur. So we just put a lone pair here, which would leave us with 2 electrons, and we'd put a lone pair here, which would leave us with 0 electrons. Okay? Does that kind of make sense? Yes or no? So now if we count our total electrons, here's 2, 4, 6, and 8. Okay, total electrons are good because we needed 8. Hydrogens are both happy because they have 1 bond. Sulfur has its 8 completed octets, so it's happy. Okay? Questions? Uh-huh.
On the back of this, it
Uh-huh.
shows for the texture.
Yep, we're not to 3-dimensional shapes yet. Right now we're just going to work 2-dimensional and then we'll start drawing in 3-dimensional. Okay, so we'll get there. Okay, here's a couple things that I want you to think of, and it's not necessarily 100% or whatever, but there's a few things, tendencies that elements like. Okay, so group 17 on the periodic table, which is the halogens, they like, in their Lewis structure, and you can write this down if you want, they like to have 1 bond and 3 lone pairs. Okay, so the group 17s, they like to, right, most commonly have 1 bond and 3 lone pairs. Okay, so if we looked at our fluorine example that we had earlier, we had fluorine and fluorine, right? Each of those fluorine atoms had 1 bond and 3 lone pairs. Okay, that's a general kind of just rule of thumb that goes with that. If you move over a group 16, they like to have 2 bonds and 2 lone pairs. Okay, again, it's not things that are set in stone, but it's just kind of some tendencies that you might want to think of or look out for. Okay, again, that's not going to follow those tendencies 100% of the time, but it likes to have 2 bonds and 2 lone pairs to help complete its octet. Okay? All right. How are we doing? Okay. So now this looks a little bit more complex for us because we don't just have 2 elements, we have 3. Okay, but we're still going to follow the same kind of sets of rules. Okay? So, valence electrons, 4 for carbon, 2 for the hydrogens, and 6 for the oxygen. Gives us a total of 12 valence electrons. Okay? The way that this is listed in order in a chemical compound gives us a clue to how the skeleton should look. Okay? It gives us a clue to how the skeleton should look. So C has to go in the middle. Carbon is bonded to 2 hydrogens, and it's also bonded to this oxygen. Okay? Because hydrogen can't also be bonded to the oxygen, right? Hydrogen can't have 2 bonds. So it looks like this. Carbon with a hydrogen and an oxygen. Okay, so the order in which that compound is written typically gives us a clue to how it's bonded, what the skeleton would look like. Okay, do we have any questions about how we put that skeleton together? Yeah, Sarah.
Does it have to be like the 2 hydrogens on one side, or can they be like wherever, as long as it's an even like?
We're okay with them being wherever for right now.
Okay.
Yeah, Zach.
How does carbon only have 4 electrons? It's only number 6.
It has 4 valence electrons, so it's got 6 in it's got 6 total, but 2 in its inner shell. That first level shell can only hold 2 electrons. After that, the next outer shell has 4. Okay? Brooklyn, did you have a question, Tim?
She answered.
Okay. All right, so now we need to bond to each of these. So 2, 4, 6. That uses 6 electrons. Now we have 6 left. So what would be, you think, the easiest way to finish this? Right, just here, 2, 4, 6. Does that work? Does everyone have a complete octet?
Yeah.
No, carbon does not. Look, hydrogen's happy, oxygen's happy. Carbon, not so much, right? It only has 2, 4, 6. So that's a problem, right? So this is what we're going to think about doing. We're going to take one of these lone pairs and we're going to bump it in to make another bond. Okay, so this means here is 2 bonds, which we call a double bond. And oxygen would have now 2 lone pairs and 2 bonds. Okay, so now let's check our octet first. Hydrogen is good. Carbon has 2, 4, 6, 8. So carbon is happy, right? And oxygen has 2, 4, 6, 8. So oxygen is happy. Okay, so one last thing, and then I'll get to you, Brooklyn. Let's count our total electrons used in our structure. 2, 4, 6, 8, 10, 12. Okay, so this is a complete Lewis structure. Yes, Brooklyn.
So how is hydrogen happy?
Okay, so hydrogen only has 1 valence electron, and it's a 1s. It's in a 1s orbital, so it can only have 2 electrons to be happy. It's one that does not complete an octet. So it only gets to be bonded to one thing all the time. Okay, so if hydrogen has 2 bonds coming out of it, you got problems, right? It should only always just have 1 bond. Okay?
So you never add to it?
Nope. Yep. That's why it can't be in the center, and that's why you could never have 2 things coming out of it, because it's only got 1 electron to give, even total, so it could never do anything else. Okay? Okay, do we have questions about this? Does this kind of make sense with the double bond?
Yeah.
Okay. C2H2. So this one has what we call multiple central atoms, right? Because if you've got 2 carbons, how do you decide which one goes in the center, right? You've got 2 of them. So what we would do is we'd set up our skeleton to look like this, C, C, right? And then we would know that an H is bonded to each of those. Okay. So total valence electrons, each carbon has 4, so this gives us 8 plus 2, which should be 10 electrons. So we're going to bond each of these together, which means we've used a total of 6, which means we have 4 electrons left. Okay, so if we have 4 electrons left, we could do a lone pair here and a lone pair here. Does that work?
No,
Why wouldn't that work?
they're not complete octets.
Not complete octets, right? Neither carbon has a complete octet. Each has 2, 4, 6. This one has 2, 4, 6. So, what if we move one of them into a bond? Right? So now we have a double bond here, and that gives us 2, 4, 6, and we still only have 2, 4, 6, 8. So this carbon is happy. This one is not. Okay?
You have to do another bond.
Yeah. Sam. Okay, so now we've got each of our carbons, 2, 4, 6, 8, 2, 4, 6, 8. Both carbons are happy, and we've used a total of 2, 4, 6, 8, 10 electrons. Okay, so this is a complete and happy Lewis structure. Okay, 3 bonds is the most you can have. Don't be trying quadruple bonds on me. Okay, 3 bonds is the most you can have. Triple bond, double bond, or single bond. Okay, that's it. If you want to look over page 188, it has some more rules, 6A and 6B, about when to add a double bond or when to take away a double bond. You can read through that if you want. I think of it more of kind of just as putting together the puzzle. So if you want to look at the written explanation of when we add a double bond, things like that, you're more than welcome to. But I really like to just kind of think of it as making the puzzle fit, right? Making the octets work, things like that. So Lewis structures very much can be a trial and error type of situation, so don't get frustrated if it doesn't work the first time. Okay?